Thanks for joining us today. Thanks for sticking around toward the end of reInvent. Really appreciate you all coming to check out what we have to say. So how many of you are here because you saw the database keynote yesterday that Swami gave with the announcement of vector search for MemoryDB? Show of hands, a couple of people. Great. How many of you are already using MemoryDB today? A few? And how many are using Redis in some other capacity? A few more. Nice. So as you know, Redis is a super popular open source key value store, but it's really so much more than that. It supports complex data types, things like sorted sets, JSON documents, hash maps, and it has built-in commands, data type specific commands that enable efficient server-side operations. So given its rich data type support and its raw performance, it is, everything is stored in memory, super, super fast. Redis is a really good option for building AI and ML-backed applications. In these applications, they tend to encode data in mathematical representations called vectors and vector embeddings that, they're representative of underlying data and they're stored in that way for efficient retrieval. Now, there's usually a trade-off between, in an AI application, the speed with which it can make a prediction and the accuracy or relevancy of those predictions. And that's really what we're going to be exploring here today. Why MemoryDB is a great option when you have large data sets and high performance demands. Vector search can power those user experiences. So my name is Joe Travellini. I lead the product management team for MemoryDB. And I'm joined today by Jean Guider, who leads the engineering team for MemoryDB. And we're super excited to go over our latest announcement of vector search, now available in preview for MemoryDB as of yesterday. So let's take a look at what we plan to go over with you today. First, I'll review vector embeddings and vector similarity search and their role in AI and ML-driven applications. I'll also talk about AWS's strategy for providing vector support across its database portfolio. I'll then go over MemoryDB for Redis. That's our in-memory database option at AWS. We'll go over how it works, some use cases, and how it might differ from other Redis-compatible solutions that you might be used to. Then I'll hand it over to Jean. He's going to go over our announcement yesterday of vector search, talk about what you can do with it, some of its performance characteristics, and we're going to show you a demo of using MemoryDB integrated with LangChain to power a generative AI application. All right, cool. So let's jump right in. So what is vector search anyway? Swami did touch upon this in his keynote announcement yesterday. But vectors are a mathematical construct. You can think of them as an array of numbers. In the length of that array, that's something that we call the dimensionality of the vector embedding. And what a vector embedding is when the data is stored, serialized and stored in the database. That's what we mean by embedding. So AI and ML applications, they encode their data into these n-dimensional vectors, and then they store them in these encoded formats for efficient speed and retrieval. That's really why they're doing that. And you can think of every data point in the vector embedding as representing a feature that the machine learning model is trained on. And each value is of that respective feature. So when you think about the trade-off between speed and accuracy in an AI and ML application, you want to be able to traverse large amounts of data very, very quickly. But there is that trade-off that the faster that you want an application to produce results, sometimes you have to sacrifice on the relevancy of those results. So where MemoryDB and vector search really shine is giving you the highest levels of performance for vector search at the highest levels of recall, 99% or higher. And what do I mean by recall? Recall is a metric that we use to measure the relevancy of the result. So vectors are particularly useful when you're interacting with foundation models, but they're also useful for traditional AI and ML techniques. So I want to show you an example of what I mean by that. Now, in an ideal world, everybody has their own custom machine learning model that's fine-tuned for their specific needs. But that's not really a practical expectation for everybody right now. It requires a lot of data, a lot of computational power, oftentimes a lot of specialized expertise, and all of those things have an associated cost. So a few years ago, some researchers came up with a technique called retrieval augmented generation, or RAG. And what that does is it enables folks that don't have the capacity or the ability to build and fine-tune their own machine learning models. You can enrich a general purpose foundation model, like a large language model, with your own data set. Something that might be proprietary, it could be an open source data set, is often domain specific. And what it does is it enhances the relevancy of the result that can be produced by these foundation models without requiring you to build or fine-tune your own. So this technique of RAG, it typically relies upon a vector database to store its vector embeddings and to conduct rapid similarity search across it. And with the recent boom of generative AI, vector databases have become more and more in demand. And that's why AWS has chosen to add vector support to many of the options in the database portfolio. So overall, it makes a lot of sense to store the vectors right alongside the underlying data that they represent. And typically that means storing it in the same database. So with that approach, it really simplifies your application architecture. It minimizes data movement and the need to synchronize across multiple platforms. It ultimately provides better performance and a better user experience. You don't need to learn and introduce a new component from a database perspective just to be able to work with or build an AI application. And that's why we've added vector support across many of the options in our database portfolio. So each of the purpose-built databases at AWS has its advantages. And that's no different when it comes to the vector support of those databases. So as an example, you're building an AI application that depends heavily on full-text search. You should use OpenSearch Serverless, which is purpose-built for that use case. And because of its serverless simple deployment model, it is the default vector database option when using something like Amazon Bedrock today. Now, if you have the need for ACID-compliant transactions, something like Aurora would be a good fit for that use case. ACID-compliant transactions along with vectors. But as you'll see, if you have a highly concurrent, high-performance demanding application, even at 99% recall or greater, then MemoryDB vector search might be a good option for you. So before I get into the specifics of MemoryDB as a service, and we get into more specifics on the announcement from yesterday of vector search, I just want to quickly highlight some of the trade-offs as it comes to the vector database storage selection. So I talked about earlier, the trade-off between the speed and the relevancy or accuracy of the results. So from a storage perspective, you can store vector embeddings in things like Amazon S3, our object storage, or in block storage like Amazon EBS, or in a database, Aurora, OpenSearch, or the in-memory database that we offer, MemoryDB. And typically, the faster the underlying storage is, the more expensive it's going to be. But there's more than just the raw performance of the storage subsystem when it comes to the performance of an AI application. Again, you have the ability to tune or configure the application to trade off speed for precision. So generally speaking, if you want more precision in your data and your results, you'll have to trade off a little bit of performance, and oftentimes a little bit of you might incur an additional cost for some of the computational horsepower involved. So let's think of some examples of this, right? Let's say you're driving down the street, your gas light goes on in your car, you hit the button, voice activate, and you say, get me a gas station within 5 miles because you've got 5 miles left according to your dashboard. Maybe you can trade off precision in the result there. You just need anything in the 5-mile radius to have peace of mind quickly that you're going to fill your tank and not break down. It might be an example of where you want to trade off relevancy for performance. But on the flip side, let's say you're building like a fraud detection application. You're a credit card provider. You don't want to aggravate your customers and your consumers. Somebody swipes their card for a transaction. You're down in Caesars or something. You buy a stick of gum. You want a precise and accurate response. That would be an example of something where you don't want to trade off the speed for the precision. You don't want to aggravate your end users. But with MemoryDB and vector search, we do want to try to give you the best of all worlds here. And again, it's really fine-tuned for when you have the highest levels of performance at the highest levels of recall. And Jean will share some benchmark results in just a bit. That's where we really shine, is at the upper echelon of performance demands and recall. All right, so earlier it looked like not so many people were using MemoryDB just yet, but lots of people were using Redis. So I do want to quickly level set about what MemoryDB is and how it works, and specifically how it differs from what you might be used to in terms of a Redis-compatible solution. So again, MemoryDB is our in-memory database option. It's the only Redis-compatible solution out there that persists data redundantly across multiple availability zones using a distributed transaction log technology. So what do I mean by that? This technology was built in-house, and it's shared with critical parts of Amazon S3 and Amazon.com's ordering systems. So whenever you write a piece of data to MemoryDB, before the service acknowledges the write, it will have guaranteed committing it to this distributed transaction log and storing it redundantly in multiple AZs, even before acknowledging the request back to the client application. So rather than adding an in-memory cache to a disk-based database system, MemoryDB has that memory-centric architecture that instead provides persistence using the transaction log. And that design allows us to provide the ultra-fast performance that MemoryDB is capable of. So let's take a look at MemoryDB's performance characteristics. So MemoryDB has a clustered architecture where you can scale out, partition your data across entities that we call shards. And each shard has a primary node that accepts writes, and it can have multiple read replicas. And like I mentioned, writes are committed to a multi-AZ transaction log. You can power up to 100,000 writes per second and 100 megabytes per second of write throughput, and MemoryDB can deliver that with low single-digit millisecond latency. And again, you're doing that persisting data. It's guaranteed to be redundantly stored across multiple availability zones, still with single-digit millisecond latency. And from a read perspective, MemoryDB stores its entire data set in memory. All reads are served directly from memory. And we do that with microsecond latency. And you can power up to 470,000 reads per second, or 1.3 gigabytes of throughput, of read throughput specifically. And MemoryDB scales vertically and horizontally. You can store up to you support up to 500 nodes per cluster and millions of requests per second. Now, these performance figures that I've just quoted, they're more general for MemoryDB. They're not specific to the vector search use cases. We're going to show you the vector query throughput in just a second. But suffice it to say, this memory-centric architecture and ultra-fast performance is very well suited to providing high-speed vector search. And what we have in preview today is one of the fastest vector experiences that you'll find available in AWS. Now, many customers have chosen MemoryDB for use cases where speed matters, where they need the rich data type support provided by the Redis API, and when they have a high sensitivity for retaining all data written. And that's both at runtime and in the presence of recovering from an operational event. So in essence, where data resiliency matters. And that might differ from some other Redis-compatible solutions that you're used to in terms of always guaranteeing that data written is redundantly stored. So the other day, our general manager and one of our principal engineers They gave a talk that dove deep on MemoryDB and went into detail on some customer use cases and case studies. It's available on demand now. You can easily find it on our YouTube channel, as well as searching the MemoryDB catalog, the reInvent catalog, searching it for MemoryDB. It was billed at session ID as DAT346, and highly recommend you check it out if you want to learn more about what made MemoryDB attractive for these customers and many other customers like them. So before handing it off to Jean to go into detail on vector search, I want to go over how MemoryDB provides persistence and some of its consistency semantics. Let's take an example where you have a multi-AZ cluster. You have your primary node in AZA, and you have read replicas in the other AZs. These replicas use that transaction log to synchronize data across the entire cluster. Now, let's say you have a client application that's writing a piece of data to the cluster. The write arrives at the primary node, and then it's committed to the transaction log. And again, before it's acknowledged back to the client application, we will have guaranteed storing it redundantly across multiple AZs. Now, all of that is happening synchronously in line with the write request. And in parallel, we're replaying those transactions from the transaction log to the read replicas. And we've chosen that approach asynchronously to optimize for write performance. Now let's take a look at the consistency semantics. So all data is stored in memory, as I mentioned, and we're doing that to optimize for read performance. And on the primary node, you get strong read after write consistency, meaning if your application attempts to read a piece of data on the primary immediately after it's written to, you're guaranteed to get the most up-to-date result. However, since we replicate data asynchronously to the replicas, if you attempt to read a key immediately after it's written to on the primary from one of the read replicas, you're not guaranteed to get the most up-to-date result. So there's a slight delay between that, and that's eventual consistency. So the transaction log does provide that multi-AZ persistence layer, and the read replicas depend upon it as a source of truth. However, the replicas are kept up to date in well under a second, a few hundred milliseconds typically. Okay, so now let's take a look at how MemoryDB provides resiliency to failures that might occur at the infrastructure layer. So now in this example, the client application is writing multiple pieces of data at once. The Redis API has a command called mset, as you're probably familiar with, where you can write to multiple keys atomically. So here we've done that, and acknowledgement happens at the transaction log layer as before. Then we're asynchronously replaying those transactions to the read replicas. And here we've set key A on the replicas. But now what happens is, in this scenario, the primary node has failed. OK, so what happens here? Now we begin the process of electing a new primary node based on the read replicas. We detect which read replica is most up to date with the outstanding transactions in the transaction log. We replay those transactions on that read replica. In the meantime, your writes are blocked. And until it's fully up to date, once it becomes up to date, it enters operation as the new primary node. And in parallel, the application is transparently redirected to the new primary, and the rest of the read replicas are brought up to date. So what you're left with here is a zero data loss failover experience. And when that happens, we're also beginning the process of bringing a new node up into operation to replace the one that failed, and it will enter the fleet or the cluster as a read replica. So hopefully that helps build an understanding of how MemoryDB works, how we provide that in-memory performance along with the multi-AZ durability. And again, it's the only Redis-compatible solution out there that uses this distributed transaction log technology for persistence. And because of that unique blend of performance and durability, we're very well suited to providing high-speed vector search, which we just released in preview yesterday. So now the remainder of this talk is going to get into the detail of the vector search preview, what it involves, different indexing techniques, the performance, and again, we'll wrap things up with a demo. And with that, I would like to introduce Jean. Thank you.
Thanks, Joe. Hi, folks. My name is Jean Guyader, and I lead the engineering team for MemoryDB. I'm really excited to talk about what we've been working on with regard to vector search in MemoryDB. So in the database keynote yesterday, we announced MemoryDB vector support in preview. MemoryDB is one of the fastest vector search experiences on AWS. It caters to AI and ML application that pushes the boundary of raw performance. With MemoryDB, you can do vector query search in single-digit milliseconds. Not only that, as you update the data, or add new data into your cluster, MemoryDB updates the index in milliseconds so that subsequent requests will include the latest result in near real time. MemoryDB scales up to tens of thousands of vector queries per second with 99% or more level of recall. As Joe mentioned earlier, you don't have to compromise ultra performance with high level of recall with MemoryDB. So now, let's go over what's available in the preview. Over the course of this year, we've had many customers reach out to us and express interest in vector support for MemoryDB. As this space is evolving very quickly, we wanted to get something useful in your hand as early as possible. We designed our preview scope in such a way so that you can get familiar with the shape of our vector API and its performance profile. You can expect that things will improve beyond what's available in preview. You can use the preview today in 5 AWS regions at no additional cost. You'll see more when I talk about getting started in a few minutes. The vector search preview is available in our latest engine, version 7.1. It supports 2 types of indexing, 3 types of measures, and it supports JSON and hash data structures. You can also do pre-filters for query to scope down the number of keys you're going to be doing a search on. So now let's dive a bit deeper in how you can actually do search. So the first thing you have to do if you want to do vector search in MemoryDB is you have to create an index. Don't worry about the syntax. I won't quiz you on it at the end of the talk, but this is the command you will send to the Redis CLI if you wanted to create an index with MemoryDB. So this command, what it means that we're going to create an index called myIndex, and then we're going to look at the keys of type hashes. And for all those keys, we look at a field called field name and expect to see a vector of 128 dimensions. The L2 at the end of this command means that we're going to do Euclidean distance search. In a few slides, we'll go over the different kind of measures and what they mean for your search results. Then if you want to change the type of search that you do, you can change only the last arguments. Like, for instance, here we're switching from L2 Euclidean search to cosine. Then now that we have an index, we can actually do some search queries. Again, don't worry about the specific syntax. If you're familiar with SQL, this statement will be equivalent to like a select stars. We'll look at all the keys that are in scope for that index, and then the 10 in that command means that we'll look for the 10 nearest vector compared to the vector that's provided as an input. The last string in this command is actually a binary format of the vector. As Joe mentioned earlier, the vectors are represented in a series of numbers. And in the preview, we also support filtering of the keys before we do the search for the index. So here we filter by a field that will be on the hash key, a field called quantity, that are within a range of 0 to 100. So what that means is instead of looking at all the keys of type hash that are in scope for this index, we're only going to look at a few keys, and it's going to speed our search results. We can also look at tags. So here we would look for keys of type hash that have a field called city that are either New York or Boston. And then remember, like this is a hash. You'll have a city field, but you have another field called field name that will be your vector. And that's what you will do vector similarity search on. So now that we've walked through how we do search and create index in MemoryDB, let's spend a bit of time talking about those dimensions that I was talking about. So MemoryDB supports 3 types of dimension. I'm going to go over 2. And I think it's easier to pick an examples here. We'll start with the Euclidean search, because it's the most natural way of doing searches. So let's pick a 2-dimension space. 2 dimensions means that you're going to have vectors that have 2 data points. So here, the first data points will be, we'll pick cars, types of cars, as our space. The first dimension will be top speed, so you can imagine numbers of the speed. And then the second dimension will be the weight of those vehicles. So you can see that you have electric cars on the top because they have a very high speed, but also very heavy due to the battery. So we're going to look at different distance measure to see how similar 2 cars are, other cars are compared to the electric car based on the different distance measure. So the Euclidean distance measure is the linear distance between 2 data points. So let's look at which car is the most similar to an electric car. So here we look at the distance around the electric car, and then the car that's the most similar would be the sports car, because that's the closest one in terms of distance to the electric car. But then if I switch to another type of distance, the cosine distance. The cosine distance look at the angle between 2 data points. So here I'm going to draw the angle between the compact car and the electric car. And the angle is very small. That means they're very similar. But if I look at the angle between the electric car and a sport car, it's very big. So it means that they'd be less similar if we were to do a vector search, a vector synonymy search using cosine. In practice, though, for all the text and search and document that generally use cosine. The third measures that we support is dot product, which kind of combines the 2. So now that we've looked at the distance measure, let's take a look at the kind of indexing that we support in MemoryDB. So we support 2 kinds. The flat index allows you to do search by going through all the vectors that are in your index. It's simple, but it's rather expensive because you have to walk through every single index. If you have a larger data set, then you can use HNSW, which is a pretty typical indexing technique that's used by many vector databases. It's ideal for a large data set, and it performs really well at high performance and high level of recall, which is ideal for MemoryDB. So let's take a look at the performance numbers that Joe was alluding to earlier. So for this benchmark, we use the big N dataset with 10 million vectors and 128 dimensions each. At 95 to 99% recall, we can achieve 33,000 vector search per second. And then we can increase the level of recall to 90% and achieve over 26,000 requests per second. We're able to achieve those kind of numbers due to the unique nature of MemoryDB, that not only our index are in memory, but also the data that we're indexing. Everything is in memory. So now that I've gone through the indexes, the different measures, what's available in preview, let's just walk through a couple of customer cases. So this is the pretty popular customer case, like RAG, as Joe mentioned earlier. In RAG, what we're trying to do is, rather than building a custom model, foundational models are very expensive to compute. They require large corpus of data and months of training, specialized skill sets, and billions of dollars in compute capacity. So it's not practical for anybody who wants to create an agent to build a custom model. So a technique like RAG was created in order to augment the knowledge base that's come from the foundational model with additional data, either fresher data or domain-specific data or private data. So what you would do is you would run those documents through a service to generate those documents into vector embeddings. And now that you have them in vectors, you can store them in a vector database, like MemoryDB. And then you will use those vectors to augment the request, so that when you do make a request to the model, you can provide additional context and more accurate answers. We'll see at the end of this talk, in the demo, how we integrate things in practice. We're also going to be providing you with the source code. It's already posted on GitHub, so you can go and have a look at yourself. We have a QR code for this. The second use case we wanted to cover in this presentation is the foundational model buffer memory. So foundational model are great at providing answers, but they don't really have any memory. So if you want to create a chatbot-like application that would go back and forth with different questions and answers, you won't be able to have context between those questions and those answers. So in order to achieve context and have a natural conversation with a chatbot, you need to store the answers of those questions as vector into a vector database. And then as you provide additional questions, you can provide the additional context from the previous question and answers that you can have a more natural conversation with your foundational model. And the third use case that I want to cover that's not based on GenAI, it's the fraud detection use case, which is really well suited for MemoryDB high performance and low latency vector search capabilities. So this is a fraud detection use case. For this use case, you would go and look at the historical data, the historical transactions, convert them into vector, store them in MemoryDB, and in real time, as customers are doing new transactions, either in a bank, credit card, or a retail type application, then you can compare the existing transactions with the history or the vector of the history of the transactions and calculate the similarities between them. If they're not similar, you would reject the transaction. If it's similar, it matches the historical pattern, you would accept it. So now that we've gone through the use case, we'll jump into, first we need to talk about how we get started with MemoryDB. So MemoryDB is available in preview, it's public, everybody can have access to it. We launched it yesterday. You can access it in the UI. You check a checkbox when you create the cluster, and you have to select, that would select the latest engine that we support. It will select the node type and the number of shards. You can add up to 5 replicas, and if you need to change the configuration because it's in preview, you'll need to create a new cluster. So now it's time for the demo to close, to wrap things up. So I'm going to come over here because I need to pause the demo. But first, let's talk about the architecture of the demo. This is similar to the diagram that we had earlier about RAG, but in a bit more detail. I know this diagram could look overwhelming and complicated. I'll assure you it's not. You can take a look at the code after. We're actually able to reuse a lot of existing building blocks at Amazon that we've built over the last few years. Here, you can recognize Amazon Bedrock. You can recognize Python embeddings to generate vector embedding from text. You have MemoryDB to store vector search, and then we use the LangChain framework to integrate everything together. On the left-hand side, we have a custom knowledge base. So the goal of the demo is we're going to be asking questions to our model and then about MemoryDB. A basic question, how to create a cluster. First, we're going to be asking the questions with a regular foundational model, and then we're going to get an answer. And then we're going to be asking the same question in a different text box through RAG, and then see how we can improve how the search result is improved, how the answer is improved. So here we just really only provided the documentation, the MemoryDB documentation as a PDF on the left-hand side, and then run it through our pipeline. So we have a video on this in the next slide. I'm going to come here because I want to pause it and comment on it as I go. So this is the code that actually takes the PDF, generate the embeddings, and store that into the vector database. Then we'll switch to another tab. It has a web UI for it. And I'll pause. OK, so I'll pause. Here we have 2 text forms, 3, but we really look at the first 2 today. The first one is the one that's going to talk to the LLM, the large language model, directly. It's going to provide an answer. And then the second one is the one that's going to provide an answer, but through RAG, using our custom, our augmented knowledge base. So we're going to ask a basic question. How do I create a MemoryDB cluster? And it provides a series of steps. I'm going to pause here. Looks and feel like the reasonable answer, right? But then when you dive a bit deeper and look at the specifics, there's a few things that are wrong or not accurate enough. Like, for instance, step 1, logging into your MemoryDB account. No, you don't really do that. To create a cluster, you log with your AWS account. Then there is another step, step 5. Select the pricing plan for MemoryDB. You don't select your pricing plan when you create a cluster. In fact, it says use pay-as-you-go versus monthly. We don't really have that as a pricing. So on the surface, it looks like a real answer, but it's full of mistakes. And then we're going to be asking the same question. But this text field will run the request through our RAG pipeline. OK, so I'm going to pause here. Here we see step 1, fix that. It's no longer the MemoryDB account. It's the AWS account. It talks about the console, the layout. It's smaller, but it's a lot more accurate. And that's how you can achieve better result with RAG on a fairly basic example. So now you can see that it's actually very simple to build. I'll go to the next slide and pause here on the QR code. So if you want to bring it up, it's on our GitHub repository. There's 2 files. It's actually very easy to set up. So I'll pause for a few seconds here so that you can take a picture. Also, this talk is recorded, so you can go back to it later and watch it if you haven't the time to select the QR code. And then to wrap things up, I'll hand it over to Joe.
Thanks, Sean. Great. Encourage you all to download the demo, kick the tires for yourselves. Check out the preview available today in 5 AWS regions. Excuse me. So again, we're super excited to make this available in preview. As Jean mentioned, you can only expect things to get better from here, more regions, more features, and we'll continue to optimize performance. But given that today, even with the preview, MemoryDB vector search does provide one of the fastest vector experiences in AWS, and again, it really shines at the highest levels of recall, 99% or more. You get single-digit millisecond query latencies, single-digit millisecond index update latencies. So one thing to add that I didn't mention earlier, as you're ingesting data into the index, as you're updating the data, we stream index updates, so your latest results are available in near real time. So please take a look. We'd love to hear your feedback. We'd also appreciate if you fill out the survey at the end of the session to let us know how we did. We look at that feedback across all these reInvent talks to help us present the best possible content in years to come. So with that, thank you. That's what we wanted to share with you today. We do have a couple minutes if anybody has any questions.